This is the third section in the modern physics topic called Energy Level Diagrams. I'd like you to open your Regents Physics reference tables right now to the charts that say energy level diagrams. The element hydrogen is shown on the left and the element mercury is shown on the right. What I'd like to do now is describe for you what these charts are actually trying to show. Perhaps you remember from chemistry class that energy levels, or principal energy levels, or shells, are the places around the nucleus where electrons are found in orbit. Now, in chemistry, you might draw the nucleus of an atom, and then you might show, for example, energy level n equals 1, energy level n equals 2, energy level n equals 3, getting further and further away from the nucleus like this. In other words, you might orient the diagram on the page from left to right. What this diagram is doing is orienting from bottom to top. In other words, the nucleus is on the bottom of the chart. Let me show you how that looks. On your chart, you can imagine that the nucleus of the atom is on the bottom of the chart, and here is n equals 1, the ground state, and the amount of energy that the electron would possess in the n equals 1 energy level would be negative 13.6 electron volts. For n equals 2, the amount of energy would be negative 3.4 electron volts. I'm just reading off the chart. All right, for n equals 3, it would be negative 1.51. For n equals 4, notice they're getting closer and closer together. It does get very difficult to read this chart. You have to be very, very careful when you read this chart. 0.85, all right, and n equals 5 would be negative 0.54. Now, I'm also going to put n equals infinity, and that would be 0. And if the electron were to jump from any level to n equals infinity, the electron would be so far away from the atom that the atom would be ionized. The electron would be lost, and since we've lost the negative electron, the charge on the atom would be positive 1. All right, so again, if you were to jump from n equals 1 to infinity, or from n equals 2 to infinity, the atom would be ionized, the electron would be lost. All right, now, again, I'd like you to keep in mind that the nucleus is down here. N equals 1 is the energy level closest to the nucleus, the lowest energy, see, negative 13. All right, and up here are higher energy levels, which are further away from the nucleus, just like you learned in chemistry. Right? Chemistry and physics work together. They teach the same ideas. Now, one of the things that I'd like to do at this point is show exactly what the difference is between the various energy levels. So, for example, if I were to take 13.6, now I'm not going to worry about any of these negatives. I'm just going to simply take the difference between 13.6 and 3.4. So 13.6 minus 3.4 means that if an electron wanted to absorb energy and jump from n equals 1 to n equals 2, it would have to absorb 10.2 electron volts. So here, this would be 10.2 electron volts. All right, now what about from n equals 1 to n equals 3? 13.6 minus 1.51. All right, the difference there would be 12.09. All right, let's do one more, 13.6 to 0.85. the difference there would be 13.6 minus 0.85. The difference there is 12.75. These are all in electron volts. All right, let's do a couple of the, let's do n equals 2 to n equals 3 and n equals 2 to n equals 4. So 3.4 minus 1.51. Oops. 3.4 minus 1.51. That would be 1.89, and 3.4 minus 0.85 would be 2.55. All right, now, the reason I've done this is because part of what we study in the modern physics topic is the idea of a quanta, a specific quantity of energy. And what you find is that the only way for an electron to jump would be to absorb 10.2 electron volts, right? A 10.2 electron volt photon, or a 12.09 electron volt photon, or a 12.75 electron volt photon, etc., etc. 1.89 would be a possible jump. 2.55 would be a possible jump. Now, these all represent specific amounts of energy for a specific photon. Any other amount of energy possessed by a photon, and the electron will not be able to jump. In other words, these jumps are possible, and any other increment is not possible. Think of it like a staircase. You can jump from the first step to the third step, but you cannot jump from the first step to 2.5. You're going to fall. All right? So specific intervals between energy levels is what can be absorbed. This is how the electrons can jump. Again, here we have the hydrogen energy level diagram. I'd like to talk a little bit about the difference between absorbing energy and emitting energy. Now, from chemistry class, you probably remember that the energy levels closest to the nucleus are the lowest energy levels. In other words, negative 13 is lower than negative 0.8. Now, these are lower energy levels, these are higher energy levels. Let me just write that in. These are lower energy levels, these are higher energy levels. Now, an atom or its electrons can absorb different types of energy. They can absorb electricity, they can absorb heat, they can absorb photons. When they absorb energy, they jump to higher energy levels, and we say that the electron is excited. So what if I were to draw an electron in a low energy level? Let's put the electron here at n equals 2. And if it absorbs energy, let's say it goes this way, right? It goes to n equals 4. So now the electron is up here. We say that the electron has absorbed energy. The electron is excited. It's in the excited state. Now, what about an electron that is going to emit energy, that is going to lose energy? An electron that is going to fall from a higher energy level down to a lower energy level. Let's have this electron up here, this excited electron, fall from n equals 5 down to n equals 2. Right? It's going to fall from n equals 5 to n equals 2. Let's see how much energy it's going to emit. From 0.54 to 3.4, simply subtract the numbers, make them positive. Don't worry about these negatives here. The difference between here and here is 3.4 minus 0.54. So this electron, when it falls back, is going to give off 2.86 electron volts of energy. Now, The interesting thing about electrons falling back and giving off energy is that the only kind of energy they give off is light. What will happen is when the electron falls from here to here, it will give off a photon of light with exactly 2.86 electron volts of energy. So, just to review what we've been talking about, when electrons absorb energy, or you could say when the atom absorbs energy, the electrons are going in this direction. They're going from lower to higher energy levels. They are absorbing energy. The kinds of energy that they can absorb would be electricity, heat, or light. Light would be in the form of photons. When they are emitting energy, when they are giving off energy, one more word here. We say that the electron is jumping. The electron jumps from a lower to a higher energy level. Now, when they go this way, from a higher energy level to a lower energy level, they can go from here to here or here to here. They don't have to go all the way to the bottom. All right? When they go in that direction, we say that the electron is emitting energy. The only kind of energy that it can emit is light, and that would be in the form of a photon. And we say that the electron falls back. All right, so when it's going from n equals 1 to n equals 3, it's absorbing. When it's going from, for example, n equals 5 to n equals 2 in this direction, it's emitting. I'd like to talk a little bit now about the type of light that is emitted when electrons fall to specific energy levels in the hydrogen atom. Again, what I'm talking about now only applies to the hydrogen atom. The chart on the left side of your energy level diagrams. This does not apply to Mercury on the right. When electrons fall from higher energy levels to the first energy level, for example, from n equals 2 to n equals 1, or from n equals 3 to n equals 1, or from n equals 4 to n equals 1. The type of light that is emitted is ultraviolet light. Each one of this photon, and this photon would all be ultraviolet light. And there's a name based upon the scientist who studied this. It's called the Lyman series. The Lyman series of emissions, let's say. Now, on the other hand, when electrons fall to the second energy level, from n equals 3 to n equals 2, or from n equals 4 to n equals 2, and you see already that I'm drawing these in specific colors, and there's a reason for that. There's red, there's green. From n equals 5 to n equals 2, or from n equals 6 to, well, there is no 6 here. Let's put in a 6. N equals 6, all right, to n equals 2. These emissions give off photons of visible light. N equals 3 to 2 would be red light, 4 to 2 would be green light, 5 to 2 would be blue, and 6 to 2 would be violet light. Now, this is called the Balmer series. Balmer, B-A-L-M-E-R, and this is visible light. These are visible light photons that are being given off. Finally, if you fall to the third energy level, let's say 4 to 3 or 5 to 3 or 6 to 3, these are going to be infrared, and we call these the Paschen series, P-A-S-C-H-E-N. All right? So the way you can pretty much remember this, 1, ultraviolet, 2, visible, 3, infrared. If you're falling down to the first energy level, you're giving off a photon of ultraviolet light. If you fall down to the second energy level, you're giving off, emitting a photon of visible light. If you fall down to the third energy level, you are emitting a photon of infrared light. You can memorize that, and it might save you a little bit of time on a particular question that asks about this on the New York State Regents exam in physics. What I'd like to do now is prove to you that indeed these emissions will give off an ultraviolet photon, these emissions will give off a visible photon, and these emissions will give off infrared. What I'd like to do is select one from each series and do the math to show the color of light, the type of light, ultraviolet, visible, or Paschen, or infrared, that will be given off when the electron falls back. Now, what I'd like to select for the ultraviolet light, we'll do n equals 5 to n equals 1. All right, that would be right here, n equals 5 down to n equals 1. We'll do that one. It's going to come out to ultraviolet light. For the visible light, I'd like to do from n equals 4 to n equals 2. It should come out green. And from the infrared, I'd like to do n equals 6, which is negative 0.38. I'd like to do n equals 6 falling down to n equals 1.51, so right there. All right, we're going to do all that math and prove that the photons given off are ultraviolet, visible, in this case green, and infrared. All right, let's do that math now. Let's see how to do that math, and let's show it all up on the board. The question that they would ask on the Regents exam to be performing calculations such as this would be a question like, what is the frequency of light that is emitted when an electron falls from, for example, n equals 5 to n equals 1 in the hydrogen atom? Or what is the type of light? In other words, is it ultraviolet? Is it visible? Is it an X-ray? Is it UV? All right? The color of the light. If it's visible, is it red? Is it blue? Is it violet? Is it green? So questions like this are the type of questions that we'd be answering with the math that I'm about to show you. Now, I want you to look on the energy level diagrams, and we're going to get the numbers, the amounts of energy for the different transitions straight from the energy level diagram chart. So, if we do n equals 5 to n equals 1, all right, we already know that this is in the Lyman series because it's going down to the first energy level. So we already know that this is going to be an ultraviolet photon. But let's prove it. All right, so n equals 5. Now I'm going to count, all right, 1, 2, 3, 4, 5. n equals 5 would be 0.54. 0.54, and n equals 1 would be 13.6. So what I'm going to do is I'm going to find the energy of the photon in electron volts by just finding the change in energy. So what I'm going to do is take 13.6 electron volts and subtract from that. Now the 13.6 is for n equals 1. I'm going to subtract from that the 0.54, 1, 2, 3, 4, 5, the 0.54 electron volts for the n equals 5. I'm just subtracting the smaller number from the larger number. So what's the difference in electron volts when an electron falls from n equals 5 to n equals 1? What's the difference? 13.6 minus 0.54, it's 13.06 electron volts. Now, if you want to identify the light, you have to find its frequency. To find its frequency, you want to use the equation E equals HF. The problem is we have energy in electron volts. If you want to use this equation with the version of Planck's constant that we have on our reference tables, the unit is joule second. So that means the energy has to be in joules. So what I'm going to do here first is convert the 13.06 electron volts to joules. So 13.06 electron volts, I'm going to use the factor label method to convert that to joules. I want to get rid of electron volts, I want joules. I look on the front of the reference tables. 1 electron volt is 1.6 times 10 to the negative 19 joules. So I take my 13.06, I multiply it by 1.6 times 10 to the negative 19 joules, and I get 2.089 times 10 to the negative 18 joules. All right, this is how many joules the emitted photon has. Now I want to find out the frequency of that photon. Again, the equation is going to be E equals HF. So if I want the frequency, it's going to be the energy divided by Planck's constant. All right, so let's use that equation now. Frequency equals energy divided by Planck's constant. All right, frequency equals energy divided by Planck's constant. The energy is 2.089 times 10 to the negative 18 joules. Planck's constant, look up on the front of the reference tables, 6.63 times 10 to the negative 34 joule seconds. All right, do that math and you find that the frequency of this photon is 3.15 times 10 to the 15th 1 over seconds or hertz. The joules cancel and you get 1 over seconds or hertz. This is the frequency of the photon that was emitted when the electron fell from n equals 5 down to n equals 1, when energy was emitted in the form of a photon. Now, we want to identify what type of photon this is. So, we go to the chart, the electromagnetic spectrum. Now, the highest frequency for the visible light is 7.69 times 10 to the 14. That's on the left side of violet. So we want a higher frequency. This is a little bit higher than violet light. Frequency of 10 to the 15th is in the ultraviolet range. So we have proven that when the electron fell from n equals 5 to n equals 1, the type of light that was emitted, the Lyman series, is ultraviolet light. We got the frequency, and it says right here that that frequency would be ultraviolet light. Now let's look at the other two. Let's very quickly do the math for the green light, for the Balmer series, and the infrared light for the Passion series. What we have here is one example of an electron falling from a higher to a lower energy level. It's falling down to n equals 2. We know from the Balmer series that this should come out to visible light. We know also from the Passion series that if the electron falls to the n equals 3 energy level, that this should be infrared light. I looked up on the energy level diagram. The amount of energy for n equals 2 is 3.4, the amount of energy for n equals 4 is 0.85. We're going to subtract them to see how much energy the electron loses. Here, n equals 3 is 1.51, n equals 6 is 0.38. We're going to subtract those to see how many electron volts the electron loses, what exactly the energy is of the emitted photon. Here we go. 3.4 minus 0.85 is 2.55 electron volts. We know we're going to have to convert that to joules. So we're going to multiply by 1.6 times 10 to the negative 19. Over here, we have 1.51 minus 0.38. So that's 1.13 electron volts. And again, we know we're going to have to convert that to joules. We want the electron volts to cancel. We want joules. These two have to equal each other. 1 electron volt. Again, you can look this up on the front of your reference tables. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. All right, let's do this math. 2.55 times 1.6, negative 19. We've got 4.08 times 10 to the negative 19 joules here. This one, we've got 1.13 times 1.6, second E, negative 19. We've got 1.808 times 10 to the negative 19 joules. Now, again, perhaps you remember that what you want to do to get the frequency is take the amount of energy in joules and divide by Planck's constant. All right, so what I'm going to do here is just take these joules and divide by Planck's constant. If this was a free response question on the Regents exam and you had to show all the work, you would have to write the equation and plug in and show all the work. All right, so we're going to take this and divide by Planck's constant. Actually, let's, okay, 4.08 negative 19 divided by Planck's constant, 6.63, 34. All right, so the frequency of this photon is 6.15 times 10 to the 14th 1 over seconds. We're going to look that up and see what color of visible light that is. This one, 1.808, negative 19, divided by Planck's constant, 6.63, negative 34. So the frequency here is 2.72 times 10 to the 14th 1 over seconds. All right, now, we want to look up what type of light this is, what type of light this is. If it's visible, we want to identify the color. This is 6.15 times 10 to the 14th. Now, I see that blue light is between 6.10 and 6.59 times 10 to the 14th. So this is blue light. And again, we went from 4 to 2. This one, 2.7 times 10 to the 14th, is less than red light. It's a lower frequency than red light, so it's over to the right. It's going to be infrared light. The last thing I'd like to do in this section is an example, actually 2 examples, one absorption and one emission, with the Mercury diagram. It's really very, very similar to the hydrogen diagram, but let's just do a problem with the Mercury diagram anyway. All right, so again, your nucleus is down here. For Mercury, they don't call it n equals 1, n equals 2, n equals 3. They label them A. All right, look at your Mercury diagram. So A is negative 10.38 electron volts. B, all right, B is negative 5.74 electron volts. We'll do a couple of them. Here's C. All right, C is negative 5.52 electron volts. D, E, F, I guess we'll stop at F. All right, so D, negative 4.95. Again, this is all in electron volts. E, negative 3.71. And F, negative 2.68. All right. So, what if they were to ask you, a transition occurs, an electron transitions from, let's say, from C to E, all right, from C to E. One of the first things you could do is to draw on your actual chart on the reference tables. Remember, these reference tables are yours during that Regents exam. Draw all over them. Whatever helps you to answer these questions correctly, go for it. So the electron goes from C to E. Now you have to be careful. C to E is absorption. E to C would be emission. You have to be careful about the wording. But if it's going from C to E, then it's definitely absorbing energy. All right, so C to E, we're going to write down that energy is absorbed. All right, now, we want to calculate the amount of energy that's being absorbed. All right, so let's find some space here. And here we go. All right, I'm going to need a little bit of space. Right here will do. All right, so to find the change in the energy, we're simply going to subtract the 2, all right, 5.52 electron volts minus 3.71. And again, you have to be very, very careful when you're reading this chart. It's very crowded. The numbers are very close together. It's very, very easy to mess this up and put down the wrong numbers accidentally. So please be very careful. What I like to do is I would like to start at the bottom and just say A, B, C, D, E, F, and put my finger on each number as I count upward. All right, so the change in energy here, 5.52 minus 3.71. All right, so 1.81 electron volts. So in order for the electron to jump from C to E, it would have to absorb 1.81 electron volts. Now, that would mean that the photon, if it were absorbing light, it would have to be exactly a 1.81 electron volt photon. Right? If it was only 1.75, it probably would not match any of these transitions. It's not going to be able to absorb a 1.75 electron volt photon. Right? It has to be an exact interval, the exact difference in energy between two energy levels, if it's a photon, in order for the electron to be able to absorb the photon and go exactly precisely to a different energy level. In this case, from C to E. It would have to absorb a 1.81 electron volt photon. Now, what if, on the other hand, there were an electron that was excited? Let's say he was excited and he was sitting up here at F, and let's say he falls back from F to B. All right, from F to B. Now, F to B. Again, watch the wording. It's going from higher energy level to a lower energy level. Energy is being emitted. Now, when it's emitted, it has to be in the form of a photon, only a photon. So, let's calculate the energy of this photon. All right, so the energy the energy of the photon, it's a change in energy, it's going to be 5.74 minus 2.68. 5.74 electron volts minus 2.68 electron volts. All right, what's the difference there? 5.74 minus 2.68. So this photon that is given off is going to have 3.06 electron volts. Now, in the previous section, in a few moments ago, I showed you all the calculations. I'm just going to go through this with the calculator to figure out exactly what we have here. 3.06 electron volts. I'm going to convert that to joules. Multiply that by 1.6 times 10 to the negative 19. So how many joules is that? That's 4.89 times 10 to the negative 19 joules. All right, now, what's the frequency of that light? Take the joules, the energy, divide by Planck's constant, divided by 6.63, second E, negative 34. The frequency is 7.38 times 10 to the 14th 1/seconds. 7.38 times 10 to the 14th hertz. So I'm going to look that up. And 7.38 is going to be violet light. This is visible light, and the color is violet. It's right between 6.5 and 7.6 times 10 to the 14th on the chart. So this is violet light. When the electron falls back and gives off a photon in a mercury atom, from F to B, the color of light, the type of light given off is visible, the color of that visible light is violet. Just a quick little summary of what we've covered in this section. The energy level diagrams show the energy levels around the nucleus of an atom. You can think of the nucleus as being down here. And this would be the first shell, the second shell, the third shell, the fourth shell. Infinity means that the electron is so far away that it has been ionized. Now, how much energy would it take to ionize an electron that starts at n equals 1? Well, it would have to go from n equals 1, 13.6, to 0. So it would need at least 13.6, and remember these are electron volts. The electron would have to absorb at least 13.6 electron volts of energy to go all the way to infinity so that it could be lost or ionized. Now, this direction is absorbing energy. Absorbing energy. The types of energy that can be absorbed by atoms are heat, electricity, and photons of light. If an atom is going to absorb a photon of light, it has to be a specific increment. It has to be the amount between here and here, or the amount between here and here, or the amount between here and here, or the amount between here and here, etc. It has to The energy of the absorbed photon has to specifically match a particular interval. If it doesn't match a particular interval, then the electron cannot absorb that energy. The only case where this seems not quite to be upheld is in the case of ionization. If you give him more than 13.6, he will be ionized. He will go to 0, he will go further, and he will be ionized. The electron will be ionized. But in all other cases, the increment must be specific. Now, this is absorbing, and this direction is emitting. the only kind of energy that can be emitted are photons, photons of light. So for example, if they tell you that the electron transitions from n equals 2 to n equals 4, take the two numbers, make them positive, subtract them, find the difference. That's the number of electron volts. You want to identify the type of light, change the electron volts to joules, then put the joules into the equation E equals HF, right, or F equals E over H. Take the joules, divide by Planck's constant, you'll get the frequency of the light. You can identify the type of light, and you know if it went, for example, from 4 to 2, that way the photon was emitted. If it went from 2 to 4, that way the photon was absorbed. I will see you in the next section.